Yeah, I'm excited to be up here in front of you all. Today we're talking about the newest application model we have on our website, which is TRISO particle production in a lab-scale spouted bed reactor. So briefly, I'll go over an introduction to what TRISO particles are and kind of why they're relevant and important today. And then I'll just discuss the objective of the application model, as well as the solution that we provide through Barracuda and the value of that solution to users. And then we'll jump into the actual modeling portion, defining the model and some key features that are necessary, and then jumping into discussion of results and conclusions. So tristructural isotropic particles, or TRISO particles for short, are widely considered to be the most robust nuclear fuel in existence today. And this is the fuel choice for the next generation of nuclear reactors. And I think these are set to come online in the next 5-10 years. So development is really being pushed both for the reactors as well as the fuel source for these reactors. So the fuel itself is here on the right. You can see there's a central core of uranium fuel. And then around this are several layers of deposited carbon as well as silicon carbide. And these layers deposit via chemical vapor deposition, much like Jared was talking about in his presentation earlier today. So several hydrocarbon feeds are fed to the reactor, and then those are pyrolyzed, and then those deposit on the surface of the uranium, as well as silicon carbide. So the advantages of TRISO particles over traditional fuels are that each particle is self-containing. So in the event of any emergency, if you need to shut the reactor down, all of these fission products will remain inside the particles themselves. So it's a self-contained, inherently safer system. And there's this idea of kind of micro-containment in each individual particle versus containing it inside the vessel itself. So the objective of the application model was to model the production of TRISO particles in a lab-scale system in a spouted bed reactor. And the specific metric we were looking to match was we were targeting growth rates consistent with those found in experimental setups. And the reason why growth rate is so important is that I think there's a pretty specific tolerance in terms of the particle size, layer thickness, and density of these particles throughout the process, and the finished product needs to meet a very specific set of specifications. So by tracking the growth rate in CFD, you can ensure that that's actually happening. So the solution provided through Barracuda is applied with the MPPIC framework in a multiphase compressible fluid domain. And we've also provided coupling of discrete and homogeneous reactions, and this would be for hydrocarbon pyrolysis, as well as the subsequent deposition onto the TRISO particles. And then through this, you can gain a deep understanding of the 3D flow fields, local species concentrations, temperatures, and most notably the particle growth dynamics, as I was mentioning. And for users, this simulation can provide insight into key metrics like the evolution of the particle size distribution and the layer thickness evolution, as well as particle entrainment. And then also, we can help with the simulation identify potential root causes, or in Barracuda, I should say, you can identify those causes. And you'll gain a full fidelity picture of the hydrodynamics and chemical reactions at high temperatures, and this is difficult to do in lab settings. The operating temperature of this reactor is around 1,000 degrees Celsius, so it's much easier to do in CFD. And then you'll also understand the effects of changing operating conditions and particle loadings. And the loadings can change quite significantly from lab scale to production scale. And that's something you can explore with the software. Oh, I forgot to play this animation. Whoops. Okay, so this is the model geometry that's included in the simulation. It's a pretty simple lab scale geometry, as I mentioned. So the total height of this reactor is 250 millimeters. The top diameter is 100 millimeters. And the bottom is conical, and that's a 60-degree cone angle. Oh, whoops. 60-degree cone angle here. And initially, 0.35 kilograms of uranium dioxide pellets are filled into the reactor. It's about 18,500 particles. And all of these have a uniform diameter of 1.5 millimeters. The boundary conditions were taken from experimental work done by Chen. And that would be the reaction temperature of 1273 Kelvin, as well as this 80-20 mixture by weight of argon and acetylene that's fed to the reactor at 26 meters per second through an inlet flow BC right in this 8 millimeter inlet nozzle. A wall temperature of 1273 Kelvin is applied through this boundary condition, and then we've specified, through a thermal wall boundary condition. And convective heat transfer and particle-to-particle heat transfer are enabled. And another key feature that's new to Barracuda version 26 is the elastic dense collision model, which has greatly helped the spouting behavior that we're able to simulate. So this is a new option in the particles tab, the particle settings. And this elastic model is very helpful when it comes to heavy, dense particles in reactors like this, like a spouted bed. And the key tunable parameter now is the angle of internal friction. Basically, the higher this value is, the more difficult it is for particles to kind of separate from themselves or slide past one another. So initially, we just looked at a few different angles of internal friction. I just want to show you kind of, it's important to get this parameter right for TRISO systems. So this is obviously not a great spouting behavior. And then when you drop the internal friction down to 20, it looks a bit better. And finally, 0 degrees of internal friction, and now you can see kind of a continuous spout and a more physically accurate behavior. So for TRISO systems, a value of 0 to 10 is recommended. These are the reactions that are included in the model. So I mentioned there's several layers deposited on the uranium particles, and these layers are deposited in 4 stages. The first stage is acetylene pyrolysis. So the pyrolysis carbon, known as carbon buffer, it's a pretty porous carbon that's deposited around the surface, and that forms the first layer. And the reaction set is comprised of 9 equations. 2 of them are equations 5 or 9 are the cracking equations where you're actually depositing the solids. And then we've also included some gas phase reactions that are actually competing with these deposition reactions here. So if there's ever any unreacted acetylene in the reactor, once hydrogen starts to build up, that will compete for reacting instead of the deposition. And these were all taken from Khan. There's also a user-defined rate coefficient. I know Sam was talking about that earlier. So this is basically what's controlling the rate of deposition in the reaction. So this value S right here is called the scavenging coefficient, and this is basically simulating like as the pyrolysis carbon, or as the carbon is formed as a result of pyrolysis, the particles in the bed that are spouting would pick that up, and that's how they grow. So this is simulating that growth right here. And it's all done in a user-defined expression. So to validate the model, we looked at the outlet compositions of a few key species, mainly acetylene, and these results are compared with those results from Chen that I was mentioning earlier at 1273 degrees Kelvin. And at this reaction temperature, the model's results were deemed reasonable. So we proceeded with analyzing the particle growth rate characteristics further. So here we're looking at the layer thickness growth rate and the mass growth rate. The layer thickness on the left, mass on the right. And this is for all of the particles in the system. We're taking an average. So at each time step on this plot from 0 to 60 seconds, what the average layer addition was overall from the initial time step. And you can see this blue dotted line here kind of represents the transition. And after about 30 seconds, we reach, I would say, steady state layer growth of about 0.156 microns per second, and that's of the same order of magnitude as the experimental growth rates. And then again, for the layer mass addition here, we're able to track that over time and after 30 seconds. And I think it's important, one thing we learned from doing this was that it might be better to include a full set of reactions instead of just one pyrolysis step, as otherwise you might end up with this over-predicted reaction right here, or layer addition right here, because you don't account for the hydrogen inhibition of the deposition. But again, you get past that transience after about 30 seconds, and that's also important because a lot of other common modeling approaches like DEM, CFD DEM, it takes a while for them to get to this state. I didn't see any papers when I was doing literature for this that even modeled it out to this far. So using Barracuda, you have the unique ability to get a truly representative view of the sustained operation of the system. These units can run for like 10 minutes or 100 minutes. So this is really helpful to be able to actually get to this steady state and model that for long periods of time. So we looked at what the average growth characteristics were like. Now we're looking at if there's any, or how homogeneous the layer growth is. Is it uniform across the bed? So if we look at an animation here of the particle size growth over time, over the first few seconds, it seems pretty uniform, and then you start to see some hot spots pick up right here. And there's a lot of unreacted acetylene kind of just hanging around here, and that's leading to the higher, I guess, growth rates there. And if you look at this probability distribution, density function for the particle size distribution, it mirrors the same thing. So at 10 seconds here, this peak, it's pretty sharp. There's not a lot of spread, so everything is around maybe 2-3 microns in layer thickness addition. But then as you keep progressing in time, you can see that there's a bit of a rightward skewed tail here, indicating that some larger particles are present, and it's not necessarily a uniform deposition. And that's highlighting one of the use cases for CFD in this application. Like I said before, you would want a uniform bed because the particles all need to meet pretty specific tolerances. So this is another way that you can use CFD to kind of analyze your results in the system and predict, okay, what kind of maybe inlet design changes do I need to make, or operating condition changes do I need to make in order to get a more uniform distribution in the bed. And another big issue with these units is entrainment. It's important to see at the beginning of the runtime and at the end of the runtime to ensure that there's no entrainment from the system. As you increase the layer mass, the volume change outweighs the mass change, so the density drops pretty significantly. From the beginning, which is this reactor right here, to about 18 minutes, which is this reactor right here, the density would decrease by about 4,000 kilograms per meter cubed. So in simulating these two systems, you can see the entrainment from that end stage system is quite a bit higher, and you end up losing about 3.6 kilograms per hour in this end stage at the same condition. So of course, you want to mitigate those losses. And this is another use case for Barracuda. We can pinpoint the root causes of entrainment and identify ideal conditions to mitigate those losses. In the application model, when you download it, you can use that and play around with those conditions and try and see what the best operating conditions are at the end stage. But that's all I have. If there's any questions, now would be a good time. Yeah.